So what we looked at in 5.4 part 1 was vectors. And a vector is basically something that can represent like a speed and a direction at the same time. So if you look at the video, you'll see an example I gave with airplanes. So the speed of an airplane and the direction the airplane's going can be represented as an arrow. Okay, the longer you make the arrow, the faster it goes. And then the direction the arrow points, that tells you which way it's going. So that's why we use arrows to represent vectors. The downside of arrows is it takes time to draw them. You need a ruler, you need graph paper. So we started to get away from drawing. What we want to look at is something like this. That's how we can represent a vector without drawing it, as two numbers. Anyone that was here yesterday, tell me what that number means? First number? Yeah.
Horizontal.
Yep, that's called the horizontal part, or the horizontal component. And how about the second number? That's your vertical part. It's called the vertical component. So, if I had a piece of graph paper, and I wanted to draw the vector 2, 3, you can start anywhere you want. Doesn't matter. Let's start right here. The 2 and the 3 are like directions on which way you go from the start point to get to the stop point. That's how you draw the vector 2, 3. Right 2, 3 up. This is also the vector 2, 3. Even though they're not drawn in the same spot, they are the same vector. They do not have to be in the same spot to be the same thing. And here's another one. As long as the vector basically has the same amount right and the same amount up for each one of them, then they're all the same thing. And that's the first thing I'm going to start with. For two vectors to equal each other, that means that horizontal components match and the vertical components match. Bring the picture back up. The horizontal component is how far right you go, and or left if it was negative. And the vertical component is how far up you go, or down if it was negative. So for this one, I go right 2, up 3. For this one, I go right 2, up 3. They're all right 2 and up 3. And since they're all right 2 and up 3, that means all these vectors are the same thing, even though they're drawn in different spots. Now, when we name a vector, we use a single letter. But the problem is letters in math are already used for variables. How do we make the letter look different if it's a vector? Talked about 2 ways we can do it. Yep.
That's the one where you like put the letter and then like the dash above it, right?
So you can put a letter and you can put an arrow above it. That's one way you can do it. And then I know that's not a variable, that's a vector. Or make it bold. Bold is how you're going to see me do it most of the time. So any question on why all these vectors are the same thing, even though they're in different spots? What's we said this yesterday too. What's the most common place we would start from? None of those that I drew are in the most common spot. Yeah, the origin is where you usually would start from. And draw it like that. But you don't have to start there. So drawing an arrow, that's one way you can do a vector. Okay, that's a picture. Another way you can do it, 2 numbers with a comma between them. And the last way, this is the way I'm going to show you right now, it's called a unit vector. So it was a little tough yesterday to get this out of people, but I think we finally got it. We talked about the word unit, and I mentioned when we did something called a unit circle. Does anybody remember what was the radius when we did unit circle trick? Yeah?
1.
1. The word unit means 1. So when we talk about unit vectors, we're talking about vectors that have a length of 1. Now, when you name a vector, you can pick pretty much any letter you want to use, except a couple. You can't use I and J. I and J are special letters. I'm going to show you in a second. There's another letter that I said I probably would stay away from. Anybody remember another letter I said not to use because it could look like something else? Well, what would be a bad choice for a letter in math? Because it would be confusing if you didn't know, because it could look like maybe a number.
O.
Yeah, the letter O. Okay, so you don't want to use O to name a vector, and you don't want to use an I and a J. Any other letter you want to use, X, M, P, Q, R, those are all fine. So here's one special vector, and this is called I. It has nothing to do with being imaginary, just the letter they pick. I is a vector that is 1 unit long, and it points to the right. Here's a picture of what I looks like. Right there. It's one unit, and it points right. I can never be anything else other than that. It has to be the vector 1 unit long, pointing to the right. So that's the first one. And the second one is J. If you call a vector J, it always means that it is 1 unit long and it points up. Always. J cannot be anything else other than that. So J is 1 unit long and it points up. That's what J looks like. So what I want to do is see how can we use I and J to write a vector. That's the last way we're going to look at writing vectors. Let's look at this one, the vector 3, 4. This is given. Okay, I just made that up. That's the question. So I'm going to draw the vector 3, 4. And then I want to see how I can kind of build that vector using I's and J's, and we're going to stack them together. So here's the vector 3, 4. Well, actually, you tell me. That's called the start. Okay, that's the initial point. It can be anywhere. I want to get to the terminal point. Which way am I supposed to go from that red dot to get to that end point? Yeah.
3 units to the right and 4 units up.
3 units to the right. 2, 3, 4 units up. There we go. Now, what I want to do is I want to start at the initial point, and I want to stack together some I's and then some J's till I land at the ending point. How many I's would I have to stack together to start making my way towards the terminal point? 3 of them. So there's one I, there's a second one, and there's a third one. So what do you think we would call this?
3i.
3i. So 3 of the i's, stack 3 of those together, plus, let's see, how many j's would I need to get up to the top? How many?
4.
Yep, I need 4 of them. So 1, 2, 3, 4. And what do you think we call that thing? 4j. And that is the final way that we're going to write vectors. That's called unit vector notation. It's basically just like we learned yesterday with these angle brackets. The difference is you take the comma away, take the angle brackets out, put an I after the 3, and put a 4 after the j. And that's how you write a vector with unit vector notation. Let's try another one. Let's try this one. Now, this time I do not have to go to the right. I need to go to the left. We know I points to the right. So, how do you think I'm going to go left? Yeah?
Negative I.
Negative I. And can you see how many I would need to get from here to here?
5.
Yep, looks like 5. So, negative I. Another one. Another one. Another one. And another one. So we had to put negative 5i. And Tony, how many j's on this one? 2. 1, 2. So think of the i's and j's, they're like building blocks. You stack them together to get from where you started to where you want to stop. And that's how you build your vector. So that's that one. Negative 5i plus 2j. Now, we didn't do anything going down, but if I wanted to go down instead of up, what do you think I would use? Yeah,
Negative J.
I'd need a negative j. So by using positive and negative I, you can go left and right. Positive and negative j, you can go up and down. You can go any direction you need to. So any questions on that one? So yesterday we looked at most of the things I'm going to show you right now. For example, we talked about how to add 2 vectors together. If you look at the video, you'll see something like this. If you want to add those 2 vectors together, and you want to do it visually, you have to line them up like that. Then you draw in a diagonal. Visually, that's the answer if you add the red and the black vector together. You get the green one. Today, we're not looking at doing it visually. I'm going to show you how to do it with just numbers. So we don't have to draw. We don't have to draw anything. So in the formulas I'm going to give you, I'm going to use 3 different letters. I'm going to use a V and a W. Those represent vectors. And alpha is going to represent a scalar. Scalar is something we talked about yesterday. Can someone remind me, when you scale a vector, what are the 3 things that can happen? Yep.
You can get bigger, you can get smaller, and then it can flip.
Yep. So it can get longer, it can get shorter, or it can flip the direction. Exactly. Now, when we do an actual problem like this one, I'm going to give you numbers for the 2 vectors. So I'm going to tell you what they are. For the formulas, I'm just going to leave it kind of generic. So the first vector has a horizontal and a vertical component. And the second vector also has a horizontal and a vertical. Again, you'll know those 4 numbers when we do a problem. So if you wanted to add these vectors up, and you were doing it visually, you have to go through what I just explained right there. And that's in the video. We're not doing it visually. all you have to do is, if you want to add two vectors together and you know all the numbers, you can add horizontal components together. That's going to be the first number. And then add the vertical components together, and that's going to be the second number. So it's like combining like terms. Combine the x numbers together, and then combine the y numbers together. Subtraction, we're going to do it now. Subtraction is pretty much the same thing. Difference with subtraction is the order is now important. So if they ask you to do v minus w, you have to do the v minus the w. Next formula we're going to look at is scaling a vector. Scaling a vector could look like this. This basically means take vector v and triple it. If you wanted to do that drawing it, you'd have to take the vector, and then to triple it, you make 3 copies of it. And that's vector v tripled. You have to put all 3 together. Well, we're not gonna sketch it. If all we want to do is scale a vector, you take the number that you want to scale by. This could be a 3, a 2, could be anything, and multiply each component by that number. Okay, so scaling a vector, it's kind of like a distributive property. You're going to multiply the number that's in front times each number that's inside the brackets, or the angle brackets. And the last formula, we talked about that symbol yesterday. Does anyone remember what it means when you put those double bars around a vector? Yeah.
Magnitude of the vector?
Yep, it means magnitude. And for people that don't understand what magnitude means, can you give me a simpler word?
Like velocity?
What does magnitude really mean? Like if you draw this arrow, how would you describe the magnitude of it? Yep.
The direction.
Not the direction. That's the other piece of the vector. So magnitude is not the direction, it's the other piece.
That would be speed.
This arrow, well, just like physically on this board, what is the magnitude of this vector? Like how would I... Yeah,
The length.
it's the length of it. Yeah, it's how long it is from here to here. So, actually I think I got it. This is perfect, this one. Look at that vector in red. How would I find, or how do you think I would find the length of that side in red based on what I've drawn here? Yeah, how would you find it? Yeah, you use Pythagorean theorem. So if you've got a vector that's on a diagonal, you make a triangle out of it, and the magnitude of that one in red would be 5. You use Pythagorean theorem. So this is the x component, horizontal. This is the y component, it's the vertical. So you square the x component, square the y component, add them together and take the square root. So this formula is really just the Pythagorean theorem. We'll try now, we'll go through one of each one of those. And that might be, we'll see. Let's see if I can leave the formulas up. So we're going to look at the vector 2i plus 3j. And we're going to write the answer both ways. We practice writing it the way we learned yesterday, and then the way I just showed you today. They're both correct. It's just two different ways of writing the same thing. So first thing is, let's see if we can add the two vectors together. Again, no sketch. So if you looked at the stuff from yesterday, we're not drawing anything. We're just writing numbers in i's and j's. Okay, so if I want to add these two together, can somebody tell me what would be the horizontal component? Yeah? 5.
5i.
Yeah, let's write it with the I and J, and then we'll write it the other way. So 5i. Okay, that's my bold attempt at making it look bold. 5i. And what about the vertical component? Negative 1j. You can just do minus j, or you can do negative 1j. And that's how you add the two vectors together. How would it look if I wrote the answer that way? It's going to be the same thing, just a little different way to write it. Yeah.
5, -1.
Yeah. 5, negative 1. And remember, do not use parentheses here. If you use parentheses, you're writing a coordinate. That's not a coordinate. It's a vector. It's 5 units right, 1 unit down. Draw an arrow. Okay, let's try v minus w. What do you think the horizontal component would be? If we do v minus w. Yep, negative I. So 2i minus 3i. We got negative I. And what about the vertical component? That's going to be the number with the j.
7j.
Yep, it's 3 minus 4. So it becomes 3 plus 4. So 7j. And if they asked us to write it with the angle brackets instead, Curtis, what would I put there?
Negative 1, 7.
Yep, negative 1, 7. Good. The next one doesn't need vector W. If you're going to add or subtract, yeah, you need 2 of them. But if you're going to scale, you only need 1. So for part C, I just want to take vector V and triple it. Visually, that means I'm stacking 3 of them together. But I just want to do it with numbers. So remember your formula. Each component in the vector gets multiplied by the number that you're scaling by. So for 3v, what would be my horizontal component?
Maybe 6i.
Yep, be 6i. And what about the vertical component?
9j.
9j. So you triple each component, and that triples the length of the whole thing. So 9j. By making it 3 times as long, did it change direction? No, it didn't change direction. If it did this before, now it does this. Still points the same way, it's just 3 times as long. And let's finish up with that one. Okay, double bars again. We just mentioned that. What do the double bars mean? Magnitude. And magnitude really means length. And when you measure the length of something, what kind of number would you never get? Negative, exactly. So the answer here is always a positive. What formula do we basically use to find the length of something? And we talked about it when I showed you guys that picture right there. Yeah.
Forgot
What?
his theory.
Yeah, the Pythagorean theorem. Yeah. Can you tell me how to write the Pythagorean theorem using my numbers for V?
It is 2i squared and
Just the two.
2.
Yeah.
2 squared plus 3 squared
Yep. 2 squared plus 3 squared.
equals, is it v squared?
Yep, that would equal the magnitude of V squared. So what do we want to do with this so we get just the magnitude and not the magnitude squared?
Square root.
Right. We want to make sure we take the square root. Okay.
Can I read the other one?
So what do we get when we simplify that? Square root of how much?
No,
13. And that answer is very different than A, B, and C because A, B, and C are all vectors. That means the answer here is like an arrow if you drew it. The answer to part D is a number. It's just how long something is. Any questions on those four things? Okay, so what we'll do is on Thursday, that's the last thing. We'll finish that. And we're not going to talk about velocity vectors. So we're not doing any of that. Might be one or two questions in there about the last thing that we didn't get to. Well, if you can't do one of those questions, we'll do it on Thursday. But what we did today should cover most of that.